All right, so welcome back to this module on computer architecture and ASIC design, and we will continue our discussion from where we left. So, what we essentially looked at in the discussion yesterday was trying to motivate ourselves why we need to study computer architecture and how historically things have evolved. And one of the things which we have looked at was basically how the sequential processor performance have evolved. And there are two very important events in that evolution which we highlighted. One was the introduction of reduced instruction set computing, and then the next big thing happened in this architectural domain was introduction of multi-core processor. And we are in the era where most of the processors are multi-core, and we are basically getting better performance because of this introduction of multi-core. And also we are solving several challenges, and going forward also we will see several further challenges need to be solved to continue this continue to get higher and higher performance. We also saw this Moore's law visualization, which highlighted that how number of transistors have grown significantly, and it's very difficult to visualize and appreciate the scale. So that's why this picture helps us to possibly visualize this better. So I'll quickly go through some of the standard Moore's law slide. If you have any question, feel free to ask. Otherwise, I'll rush through some of these slides. So this slide again is a very standard slide which shows the rate at which the different number of transistors, or the number of transistors actually, or the complexity of the chips, which is represented as number of transistors, increases for both memory as well as CPUs. And as you will be knowing that processors, the number of transistors increase little slowly compared to memory, and this is famously known as the Moore's law. In case of microprocessor also, if you look at this trend and the number of transistors, this trend very much follows. So these are all Intel processors, and if you see how their number of transistors in those processors have grown, it clearly shows that the number of transistors has doubled every less than 2 years at that rate. So basically, the clock frequency, as I was also highlighting in the last discussion, that frequency was constantly also improving, and it was doubling of almost every 2 years. But then if that trend would have continued, then Intel basically showed that the power dissipation would have really in a bad situation. So you are looking at like early Pentium series, and they were basically burning around, or power dissipation was around 10 watts, or in that range, and it would have gone very quickly to hundreds of watts. And this was constantly going upward. And if this trend would have continued without any modification, then these are the power numbers which we are looking at. So you see that by early 2000 we would have in the range of hundreds of watts, and then kilowatts, fives, tens of kilowatts, in that range. So which results in power density numbers which are really very very scary. For example, if you look at these power density numbers, the power density numbers are equivalent to basically a hot plate in the. Okay, so let me just see. So yeah, for Pentium 6 P6, it was in the range of hot plate, so you can basically pretty much cook your food on that will be the power density. And if we would have gone further in that direction, then it would have been as hot as a nuclear reactor, uh, followed by rocket nozzle, and eventually like the power density of surface of sun. So basically this again, Intel highlighted this power wall problem in early 2000, and that's when the researchers set together and the concept of multi-core came in. So we are in this era of multi-core, where to keep up with the demand of computational power, we have, instead of one core operating at a very high frequency, we have multiple cores, and they are operating at relatively low clock frequency. And this is what has been adopted widely by the by commercial space as well as research domain. And there are many companies like Tylera, Tylera right now it's named, it is bought by EasyChip, which generates this hundreds of cores system for networking, cloud computing, multimedia applications, etc. There are some single chip multi-core processor which are shown in this slide. Uh, uh, Adaptive's Epiphany is a co-processor for mobile devices for primarily gesture recognition, and it has 64 cores. Tylera, as I mentioned, they have hundreds of cores. They have solutions for different platforms like networking, cloud computing, multimedia, etc. Intel, this 80 core processor, this was the first uh, 80 core research chip produced by Intel, which could sustain, I think, 1 teraflop operations in the research lab. Then Intel has this single chip cloud computing, Intel's Night Landing, so which also has more than 50 cores. So this is the time when multi-core was becoming popular, and Professor Anant Agarwal from MIT, is also a founder of Tylera. He came up with this corollary of Moore's law, which suggested that number of cores will double every 18 months. So this prediction was made in early 2005, 2010, in that range. But as we can see that the number of cores has not doubled every 18 months because of several reasons. Some of them are related to basically the challenges challenges associated with parallelizing a task. Uh, and also there were some other basically sharing of information. So here, as you make or distribute your task into multiple processing elements, your interconnection network becomes very critical. So your transistors can switch fast, but your data movement is the biggest challenge, and that's why a lot of research is going on. So whether you look at the stored program model, where memory and processor need to talk to constantly, and this problem becomes even more difficult when you have too many processors and also too many memories, where you have data which some of them will be shared. So how do you know that who is having which copy, and how do you maintain coherence? So these are some of the challenges which are there, and a very active research is going on to address some of these challenges. So we are in this era of many core systems, and it is at a very early stage of many core processor evolution. Very soon, right, just like our mobile phones are invariably becoming multi-core. You will have either quad-core or octa-core kind of processors. Mm, uh, Very soon we will have almost every processor we deal with. We will have they will have multi-core, multiple core, and maybe they will be doing very unique stuff. We are at a very early stage of this many core processor evolution. Also, if we look back and see how things have evolved, it's very fascinating to observe that the first 1 teraflop processing power was achieved by a supercomputer in the year 1997, which had which looked like this. So it had 72 cabinets and these many Pentium 2 Xeon processors, and it took a large hall to house that kind of a computer. And in less than 15 years, basically we have a single chip solution, Intel's Knight's Corner, which was designed and fabricated in 22 nanometer technology, and it could sustain the same performance, 1 teraflop. Whatever we are seeing is just at a very early thing. So having supercomputing power in our handheld device is not something which is kind of fiction or not realistic. Because if you just look at the history, you will see that the way things have evolved, they are very encouraging, and only time will tell that how things will evolve further. So it's very interesting phase. Okay, so and there are a lot of research problems, so some of them which are related to power management. So obviously the exascale computers consume huge amount of power, so how to reduce that. The other problems are like basically when you have this big and complex processor, how do you make sure that everything is coherent, because you are doing lot more stuff at different parts of your chip. So how do you make sure that things are coherent? The data movement is efficiently happening, because that consumes a lot of additional resources. And apart from that, basically how do you make sure that the housekeeping stuff inside that big chip is done in the most accurate manner. uh, Also the general general steps of designing an SoC, etc., become much more important. For example, verification. um, since you have this big a chip with tens of billions of transistors, and so many variabilities or so many things which can go wrong, how do you ensure that whatever you have designed will work as expected? So that's where your verification becomes very important. But basically the functional verification has its own limitation, or basically prefabrication verification has its own limitation. You will not be able to verify every part of your chip uh, through these steps. So that's why post silicon verification becomes very important. But again, post silicon verification is a time consuming, resource consuming step. So how do you optimize that and also do it in a timely manner? Because you can't take, like, say, months to do a post silicon verification of a processor, otherwise it will lose the market. So all these challenges are there, and there are many more which many research groups are working on, including our group. Okay, so one interesting change in this when we moved to multi-core happened was, in the last lecture I'll try to also highlight when we talk about SoC design trends, etc. But I'll very briefly talk about it. So when you had one processor and its peripheral, they were connected through a bus. So bus is much better manageable for a small system. You can broadcast stuff very easily, but bus is not a scalable solution. So by scalable solution, I mean like it's a shared resource. So if one peripheral and CPU, or let's say two peripheral, want to use the bus, then nobody else can use the bus. So it was okay for small systems where there was one CPU, one memory, some peripherals, etc. It was okay. But when you have multiple CPUs, so let's say 16 core CPU you have in this example. Now bus is not a scalable solution, because if let's say any one pair wants to communicate among themselves, all other processing elements will have to wait for the that transaction to be over, and then only they can use the bus. So even if you have compute power, because your data is not available, your performance will suffer. So to address that, the concept of network on chip was introduced. So what is network on chip? So network on chip says that, okay, you do not use bus, you use a network to establish communication inside the chip. So to establish that, you have a switch, along with it, basically you have a switch, along with it you have an interconnect, and all the communication part is taken care by this combination of switch and interconnect. So basically this processing element will only do the computation. The communication part, so the after computation, it will tell that, okay, this is the destination where this packet or data need to be sent. Now this switch will get this information, it will figure out how to route the information to that destination, and it will do it on its own. It will not consult the processing element. So it decouples the computation and communication, and that way it becomes like a scalable and modular solution. And whenever you need to design systems which have more than, let's say, 16 or 32 cores, you have to use something of this kind, network on chip, because without this network on chip infrastructure, you will not be able to design multi-core systems. And all the uh, multi-core chips which you see, if they have more than, let's say, 16 or 32 cores, invariably they use network on chip. And all different companies, whoever is interested in this kind of high performance computing and single chip solutions, they are investing heavily on this network on chip of late. The research started on network on chip in early 2005, in that era. It was mostly academia which was researching on it, apart from Intel and few other industry. But now every other company is looking for experts with network on chip kind of knowledge. So it's again a very important enabler for multi-core chips, and we are extensively working on network on chip related research. Now, how actually network on chip help us in achieving our goal? So let's say this is our source node, this is our destination node, and the after computation, the message need to be sent from here to here. So the packet will move from the source to the destination through these switches, and it will be a multi-hop communication. So after the first hop, it will reach to this switch, followed by the switch will basically decide that depending on the destination, which output port the packet should take, and then it will move it to that particular direction, and so on, and it will reach to its destination. So all these things are fine, but only challenge is this infrastructure. The communication infrastructure is very uh, or very significantly power hungry. It consumes a significant amount of total chip power. So your there is a scope of basically getting better results, better improvement, if we can make this network on chip more power efficient. So a lot of work again is going in that direction, and our group is also working on that. So I'm going fast because I think we need to start discussing about some of the important stuff, like difference between ISA and microarchitecture, and then pipelining, etc. So, but if you have any questions, these are the work or research work where we are extensively working on. So I can give further details, maybe offline or through in some other time. Okay, but if you have any quick question, feel free to ask. I can briefly talk about it. All right. Okay, so now we are going little deeper into our discussion on architecture and.
So just one question.
Sure.
On the NOC part. So for the traditional process, we already have kind of standardized systems. At the same time, we understand NOC is evolving, right? But are there any known standards for the routers and links to be used or to be architected in the NOC field?
See, there are there are few thumb rules. I would not call them standard. So generally, you have either a 64-bit processor or a 32-bit processor. So depending on that, you will define what will be the link width you will be using, and then the router. So router, again, you want to make it as simple as possible, and many things depend on the kind of topology you select. So the topology I shown was a mesh topology. So if you have a mesh topology, then generally routing is done using, let's say, techniques like XY routing and so on. So your switch will be able to switch will be routing the packets using the basically it will move in the X direction first and then Y direction after the X direction has been covered. So these are kind of thumb rules which are used. Now, how complicated you want to make your switch? For example, whether the switch will be pipelined. If it is pipelined, then how many stages it should have. Um, will it have some intelligence? For example, do you allow adaptive routing? Do you check like how do you maintain quality of service? For example, if there are some high priority message that need to be delivered, do you have the capability to deliver them separately, or assign priority to certain messages? How do you maintain flow control? For example, let's say this switch, how far it can see in the downstream. So all these things are kind of a trade-off. So you can add as many things as you want, but that will have overhead, but maybe it will give you better performance. Whereas, yeah, the other way would be you make it really simple and you compromise on the performance a bit. So, so these are the things. So there is no. So there are very few commercially available products. For example, I think ARM is in the process of having this IP. There are companies like Arteris. They have NOC IP, which is commercially available. So most of them, they give this flexibility to the user. Let's say you want to design a multi-core system, you tell the topology, you tell the routing you want to use, that IP can very quickly switch, basically can select which routing you want to use, which kind of topology you are using, and depending on that, what kind of bells and whistles you can add to it. So it's in that way quite flexible. I hope that answers your question.
Yes, sir. Yes, sure. So one more thing on the same line, sir. So when we say that the multi-cores are connected by the switching and the routing logic, right? Is it the same logic that is replicated multiple times, or is it a single element that takes care of the multi-core switching? inside. Like if I look at the picture there, it's kind of replicated architecture there.
Yeah. So these are physically replicated things. So these are not logical replication, because then they will become bottleneck. So you want to have dedicated switches or routers connected to each of the processing element through some network interface. So basically you have a processor, it is connected to the interconnection network through a network interface. Uh, very much like what we see in our basically this the connectivity which we get through, let's say, switches and in the buildings. So you have a switch or access point somewhere, that access point is connected to a switch. So similar to that, you have your processor that through network interface gets connected to that switch, and then switch takes care of how your data needs to be routed.
Okay, sir. So, is it right to say that we understand this switching as a part of physical layer, or
Yes, you can. I think it is a fair thing to say. It's part of physical area.
okay? Yes.
Okay, so there are few questions on the chat box. What programming language do you use in designing NOC? So see, ultimately you want an RTL, right? So you need that RTL for physically implementing that NOC. But for logically looking at how it will perform, to check different kind of, let's say, routing and how it will impact your network performance, etc. So for that there are simulators like NOCSIM written in C++. Uh, these are widely used. So basically one step is basically you model the system, and you can, for modeling, you can use system C and see how this performance will change for your different design decisions. Other thing is, if you want to actually implement NOC, then you have to generate the RTL, and we have worked on both this direction. We have right now, we are just giving some final touch on a tool which will give you the RTL of NOC if you provide your requirements. We are fine tuning it, and once things are done, we will make it available as part of open source tools. Yeah. Then NOC is a hardware thing. So any RTL design and verification will work. Okay, so somebody responded to that. Great. Um, all right, but there are strengths to every language. I want to know also if they are using TL Verilog. Okay. So far we have tried with RTL and basically for modeling we have used C and to some extent MATLAB also. Yeah, but there is no, as long as you can understand the logic and what needs to be implemented or modeled, you can use any language. That's my understanding. Okay. Should we go ahead?
Yes, sir. Just one final question is that when we understand there is no general architecture, but still it is evolving. But as a kind of a basic abstraction for the link and the router stuff, right? Uh, does all of these implementations work on a kind of a credit token based logic? Because I have seen it in some papers and studies that
Yeah,
it. Okay.
mostly because see, you have to have some kind of a flow control. So if I go back to the figure, let's say this router wants to send something here, but if there is a congestion already, then even if it sends, it will not reach to the destination. So it has to have some understanding that what is there downstream. Also, once it sends, it has to have some kind of acknowledgement that whatever I have sent, it has reached to the destination as expected. So that's where this credit flow comes in. So you are correct. Most of the communication follows this kind of flow control mechanism, and I think it will be a little unfair to say that there is not much standard. So it's pretty much like everyone knows what need to be done, and you pick and choose which all things you will be needing. So in general, for most of the computer architecture related thing, it is like that only. You can do it 10 different ways, and basically the pros and cons of those 10 different ways are not drastically different. Basically there will be slight advantage here and there. It's not like one technique is much better than all the other 9. But you have to look at your resources, look at your performance which you are looking at, and then take a call that which one will be best for you. So yeah, it's like designing interconnects, right? So I can select that, okay, I'll instead of a 32-bit bus, I'll have a multiplexer or something. So whether I put a multiplexer or design that 32-bit bus altogether, as a designer I have to take a call. So similarly, this switch, what it will be doing, it's very well known that, okay, you get the data from input port and you look at the destination, and accordingly you select which output port the data should go out to. And that's the purpose of this switch. You check few things before you push it out, and if everything is fine, then you push it out and start processing the next one, and so on.
Sure, sir. Thank you.
Thank you. Okay. All right, so let's move ahead and look into the or start discussing about the difference between architecture and microarchitecture. So I think in the beginning of the class there was also one question that which was related to this. So architecture, or basically different books call it differently. So architecture is nothing but instruction set architecture. Now, what instruction set architecture? So we saw that there are two different abstraction layer. One is instruction set architecture followed by the microarchitecture. So in instruction set architecture, at a very top level, if you want to understand, basically it's an abstract layer which is provided to the software designer, programmer, so that uh, they can assume, or they can basically get some idea that what kind of facilities I will be provided, so that my program can exploit that. So it's a theoretical definition of the hardware that will be executing the program written by a programmer. So for the programmer, he needs to know some information about the hardware which can be exploited while he writes his program, he writes his basically designs his compiler, etc. Now another thing which is very important is that instruction set architecture does not change very frequently. It is something which is very static. Very rarely you will see that there is a change in instruction set architecture. So it provides the information, like let's say how much memory I can assume. So basically, if my the instruction set architecture tells that, okay, uh, uh, your address bus width is, let's say, 32-bit. So that means that you can have a address space in your program which is as large as 2 to the power 32. So you can address 2 to the power 32 different memory locations or memory words from your program. It also specifies that, okay, you can assume, or you can take that there are, let's say, 16 general purpose registers. So what are these general purpose registers? So I'm not sure how much what is basically what are the backgrounds of each one of you. So I'll just very quickly talk about this general purpose register. So we know that our programming model is a stored programming model. So this is our CPU, and somewhere we have memory, right? And by design, our CPU gets data and instruction from memory, executes it and sends it back to the memory. Now it has been observed that every time you need to access memory, it is time consuming, and also it has significant overhead in terms of the amount of power you need to burn and all these things. So, and also it slows down your process, because your CPU possibly can, let's say, work at a clock frequency which is, let's say, 1 gigahertz, whereas for accessing your memory, I'm just giving some numbers randomly, but generally the practical numbers are also in that ratio. So for accessing memory, you can basically the highest speed at which you can access memory is, let's say, 100 megahertz. So in the CPU, I have a ALU. So ALU will be basically, let's say, waiting for two of its operands so that it can perform the function and get you the result. But these two operands will come from memory. So you essentially have to wait for that two operands to be available, and then only you can do the work. So though your CPU can work, can be clocked 10 times faster than what you are currently operating it at, but since your data is not available, so there is no point in running this CPU faster. So to address this issue, what could be done is basically what has been observed, that you can create a register file inside or very close to the CPU, basically in the vicinity of the CPU. So this register file is nothing but basically bunch of registers which can hold, which is nothing but memory, right? So they can hold to your operands which you need to work with. For example, let's say you are fetching few operands or variables, let's say A, B, and C, and it has been observed, because of spatial locality and temporal locality of the way we access data, it has been observed that if you are accessing a particular variable right now, it's very likely that you will be accessing that variable again, and also you will be accessing, so that is temporal locality, and you will be possibly accessing the adjacent value. So basically, if it is an array, so if you are looking at currently the first element of the array, it's very likely that you will look at the second element of that array also in your program. So because of all this information, it makes sense to have some memory very close to CPU in the form of registers, which are in terms of implementation, the overhead is little bit more, basically, but registers generally are implemented through flip-flops, etc. But they are very fast to access. So now let's say I know that my program will be dealing with these three variables very frequently. So I will just store these three variables in my general purpose register. So I'll reserve this three general purpose register for those three variables. So every time CPU needs to access them, they can directly be accessed from my general purpose register. So these are general purpose registers. So that means I can put anything, any generic variable there. So now, how many of such registers are available in your processor? That is also specified at the instruction set architecture. Now, instruction set architecture says that you will have, let's say, X number of general purpose registers. Now, it might happen that, okay, let's say I am following an ISA where it is specified that there will be 16 general purpose register. Okay. Now, how do I implement this general purpose register in hardware? That is a completely different decision. So, so let's say the ISA says that there should be 16 general purpose register. Now I am a microarchitecture designer. So I know that my microarchitecture has to follow this ISA. By following this ISA means what? Means that any program written for this ISA should run on my hardware. Now, to achieve that, I can do few things which the program will not realize that I have done differently on the hardware. For example, the program only knows that these are general purpose register. I will store my variables in this general purpose register. Now, in the hardware where I define this general purpose register is completely my call. I can define this general purpose register in the memory itself. Let's say I don't have any expertise or the resources to build those general purpose register closer to CPU. So I just declare a part of memory as my general purpose register. Now my program will run, but it will suffer because the access to general purpose register will be slow because these general purpose registers are implemented in the memory itself. So these information, so how much memory I can assume. So these are all theoretical information. How many registers I have, the kind of instructions I can deal with. So for example, whether I should be able to operate floating or operate on floating point numbers, that will be determined, that will be specified in the instruction set architecture. Also, how do I handle interrupts? For example, let's say I am trying to access some out of bound memory, or let's say there is a divided by zero kind of error. So they will generate interrupt. Now the ISA will tell that, okay, these events will be generating interrupt. But how that interrupt will be generated and at what particular basically instance that will be triggered, etc. Those are all microarchitecture level decisions. So these information you are giving as a just like different standards tell you that, okay, this is how things will happen. But actually how things are happening, that will be determined by the microarchitecture. I'll give you one more possibly more intuitive example in a while. Similarly, basically how your input output. So whether yeah, basically you can have a UART for input output, or basically whether you will have parallel inputs, parallel outputs, or some serial input output. So all these theoretical decisions will be specified in the instruction set architecture. The data types, for example, whether you will be able to handle single precision numbers or double precision numbers, whether you can handle, let's say, floating point numbers or integers only. So all these things, and what will be the size of the data. So whether you can deal with 32-bit data or 64-bit data. So all these things will be specified at the instruction set architecture. Now your instruction set architecture again might say that, okay, you will be able to deal with 64-bit data. But while you are implementing your hardware, basically you realize that 64-bit will be too much to implement. So what you can do, you can give the impression to the program that, okay, you are handling 64-bit, but internally you are breaking that into 32-bit and doing it in a sequential manner. So all these things are done at the microarchitecture level, but that will not be reflected at the instruction set architecture. So one analogy I try to give in this case is something like many of you have been or even now maybe students. So you might have seen while you are in a hostel or in a campus, there are mess inside the campus where you can go and have your food, lunch, dinner, etc. Now, when I describe about a mess to you, so that's it. Basically, instruction set architecture or theoretical definition of a mess. For example, let's say I claim that, or I tell you that in triple IT we have a mess which caters to all the food requirement of the students and other people at triple IT. Now you can visualize that, okay, there is a mess. Now, of course, you will have some queries in your mind. For example, let's say, and I ask you that, okay, next time you visit triple IT, you have to have food in that mess. Now, essentially, what you will start thinking that, well, okay, I am a vegetarian. So, is it a vegetarian mess or a non-vegetarian mess? Or let's say somebody is non-vegetarian, he might have this question in mind. So now I, as a basically, if I am trying to describe that mess to you, so I have to give you this information. So whether only veg or non-veg kind of items are served, then I'm trying to find out appropriate analogies. For example, let's say the memory could be analogous to like how big is this mess. So if triple IT has a population of 3,000, then during the peak hour, if I go, what will be the waiting period? So that will be analogous to how big that mess is. So possibly the memory. Now, also, so I can give you this information so that, okay, the mess can handle, let's say, 500 people at one go. So from that information, you can guess the number of registers. So basically, the analogous could be how many, let's say, different food counters are available. So let's say if the crowd is too much, then do you have like multiple counters where, like, if this counter is very crowded, I can move to another counter. So these are, so see, we have not yet gone to the mess, or we are not talking about how that mess will be designed, but we are theoretically discussing what the mess structure should be. Now, for the analogous to different kind of operations, so maybe one crude analogy can be like what kind of cuisines the mess serve. Is it only North Indian food, South Indian food, maybe some Asian food? So do you have different cuisines or only one kind of cuisine is served? So that could be different operations the mess handles. The analogous to or analogy to interrupts could be like what kind of, let's say, um, uh, uh, fire. So do that mess have a fire alarm kind of thing? So let's say if something goes wrong, if it becomes too crowded or there is a fire incident, is there a proper mechanism to handle that? So so I'm theoretically describing that mess. Let's say at Triple IT Delhi, there is no mess, but I am trying to tell a possible vendor that if you want to build a mess, these are the things I want. Okay. Similarly, how do you get to eat there? So do I need to have prepaid coupons to access the mess, or I can just walk in? Similarly, the data types again could be like related to size, like how many people at once can come in, what will be the how many counters should be there, etc. So what we have done, let's say we are describing the mess to a potential vendor who will build this mess. So now with this information, I have a clear idea about what this mess is capable of doing. So, and this is my instruction set architecture. I have not yet, basically, I don't have any mess yet. I have just described what that mess is. So if some user wants to use this mess, when this mess will be built, they can expect all these things that, okay, this many people it can handle, this different kind of cuisines it can handle. I can get some idea about whether it's veg, non-veg, whether some safety measures are taken, whether I should go and pre-book my meal and then only walk in, and how much crowd, basically how efficient that mess will be, how many people it can handle, and so on. So these theoretical description I have given. Now let's say some vendor takes this challenge and he comes and says that, okay, I'll build this mess. Now the task of microarchitecture starts. So while the guy starts building the mess, he will have several options. He will think that, okay, basically there are different trade-offs available to him. He will see that, okay, if I need to cater to 3,000 people, he can do some statistics and find out that at any point of time, not more than 500 people will be there in the mess. Now he can again take a call that to handle this 500 people, do I build a big hall which can handle all the people? Or basically I build a hall for which can handle only 100 people, and I have seating arrangement outside the mess so that people can take the plate and walk out and eat at their convenience, etc. So now he's taking decisions which has implication in terms of cost, in terms of efficiency, in terms of speed of service, etc. So very similar to, let's say, my ISA says that I can handle the address space I am having is 32-bit. Now, do I physically build that 2 to the power 32 memory for my hardware, or I assume that, okay, I will never use that much memory in any of the program. So why do I build that much memory? I just physically build maybe let's say 2 to the power 10 byte of memory physically and map it virtually to all the 2 to the power 32 addresses. So basically there will be a step where basically physical virtual to physical mapping will be done. So the programmer, he may assume that, okay, I have 2 to the power 32 memory spaces, but I have physically 2 to the power 10 only, and I'll be intelligently mapping them in and out so that the programmer will not know that hardware is much smaller. So similarly, when I describe the mess, I have given specs that, okay, it should be able to handle 3,000 people. But the guy who is building this mess, he knows that, okay, at a time not more than 100 will show up. So I'll build a hall which can only accommodate 100 people. And if it spills over, then I'll have some additional table chairs outside. So these are basically implementation design decision. So he has to take a call and find out trade-offs between speed of operation. So basically how fast as you walk in, how fast you get food. Now to make it really fast, you have to spend more money. So the guy who is building this mess, he is to have more number of counters. So more number of counters means more number of people has to be employed so that they can make sure that all the counters are having all the foods all the time. So that's a trade-off. Now, from the management, it might be asked that, okay, come what may, the waiting time for a student in the mess should not be more than, let's say, 10 minutes. Now, in that case, even if it is costly, the mess vendor has to provide additional counters if it is not meeting that time. And of course, if you do more work, you will be burning more energy. So that's there. So basically, these are design decisions. So some examples here are mentioned in the microarchitecture front are like pipeline depth. For example, now in the mass implementation, let's say I you have 5 different items to be served. Now all these 5 items could be put together, and one person walks in, he takes his sweet time to take all the 5 items, 6 items, and then he walks out. So maybe this whole process takes, let's say, 5 minutes. Okay. Now the alternative to that could be, let's say the counter is arranged like this. There are 5 items kept with their independent spoons. So one person walks in, takes the first item, move to the next counter. The second person walks in, and ultimately this guy walks out after taking all the items. Now, if you look at in during steady state, you will see that if one item takes, let's say, 1 minute to take, so every 1 minute, one person will be coming out of this queue. So this is much more efficient compared to this approach. But in this approach, you had to put more resources in the form of, let's say, additional spoons, the additional containers, and so on. So basically, here you have created a pipeline, and this is not a pipeline situation. So this takes 5 minutes, whereas basically from this pipeline, one person comes out every 1 minute. So it will be able to handle queue better. Now, there could be something intermediate. Let's say instead of 5 stages, you can decide that, okay, I don't have that many containers, so I'll put in 3 containers 5 items. So that is basically the decision you have to take. What will be the depth of your pipeline? So how many different stages you want to make? If you want to make more number of stages, your time per stage will go down. So eventually your efficiency will be more, but you will be spending more in terms of your infrastructure, etc. Now the number of pipeline, the equivalent to the number of pipeline is basically how many counters you have. So you can have one counter, then everybody has to get food from that counter only. You, on the other hand, you can decide to have several counters. For example, one for veg, one for non-veg, one for different cuisines, etc. So if you have multiple counters, then of course your the crowd will be distributed and the service time will become better. But of course, that will require more resources. Now, some concepts like cache, etc., we will briefly talk about later. But just to give you some, again, crude analogy, let's say in this counter, so one of the counters serves roti, freshly cooked roti, and the guy who is cooking this roti. So in one example, it could be like that. He is just standing here and cooking the roti. So every time the container is empty, you will get roti quickly because he is preparing it here only. So as if you have cached the thing which you need nearby you. The other option could be the guy is cooking in the kitchen. So once roti is out, roti is done, or let's say every time roti is over, so you have to send a request. This guy will come and take his sweet time and serve, basically provide roti. So that will be a very long process. Of course, in both this process, when in this case where you are putting this guy close to the counter itself, you need additional arrangements because you have cooking something close to the counter. So of course you need to have additional burners and all those things. So it will require cost. Now the mesh vendor has to take a call that whether he wants to incur that cost or he will be going by this way. So see, when I theoretically described you this mesh, you had no clue about all these things. You only knew that, okay, there is a mesh which can serve this many people, and so on. It can serve this kind of cuisines and all. But when you came in and you were physically going through this mesh, then you realize that, okay, it has a 5-stage pipeline or a 3-stage pipeline. It has 3 different pipelines, for one for veg, one for non-veg, one for maybe other things. Also, it has this inbuilt, basically it has the memory access as cache. So basically I can get whatever I need quickly. So basically equivalent to, there is a guy who is cooking the roti or preparing the roti just next to the counter. So I can get roti faster compared to this situation where every time I need a roti, I have to wait, and that will take some time. So so this is the difference between microarchitecture and architecture. Similarly, what will be the floor plan of the mesh, which is basically equivalent to silicon area, the power consumed. So basically, again, the resources will determine how much power it will be consuming. Execution order, this is very important. Now, do you in the mess, do you enforce that whoever comes in first, he will be served first? Or let's say there is a large queue for vegetarian people and there is a very small queue for non-vegetarian people. So do you allow the non-veg to basically jump the queue and get the food out of order? So that is what is called execution order. So these are very interesting things. The equivalent is, let's say you have a bunch of instructions. Now some instructions maybe are waiting for something to be done, and that's why the instructions which are subsequent to that, they are also stuck. Now can I find out that the subsequent instructions, whether they are basically independent and can be executed out of order, and if so, then can I have the capability to execute them out of order? So of course that will increase complexity, but you can assume to get better performance. Similarly, the bus width. So bus width is equivalent to, again, um, uh, possibly let's say how many people you can handle at a time. So let's say do you allow one person to enter the mess at a time, or you allow, let's say, 5 people to enter the mess at one time? So that will be determined again by basically the things you can handle inside the controller at the same time. ALU width is equivalent to basically how big the number you can deal with. So whether it's a 32-bit number or a 64-bit number, though your ISA says that it's a 64-bit number, and in the implementation, actually you can divide that 64 into 32 and 32 and do all your arithmetic operations uh, uh, like that. Basically in 2 steps instead of 1 step. So all these things are design decisions at the microarchitecture level. So one thing I would like to highlight is that uh, computer architecture is all about trade-offs. You can implement this ISA, which is described in hundreds of different ways. But which way you select is dependent on the trade-offs you need to take care of. For example, let's say you are trying to design a processor which will be used in IoT application. So basically some edge, on the edge you want to do something. Now for that, you really care about the battery life. So you want that battery to last for maybe months. So in that case, you would like to prune everything else and only stick to the basic stuff. And for that, you will be implementing your ISA very differently compared to, let's say, you are designing a processor for some workstation. So in that case, the workstation is always plugged in. It has elaborate cooling mechanism. So you want performance at that time, at that kind of scenario. So there you don't care much about power, possibly also cost. So you focus on speed primarily. And that time your design decisions will be very much influenced by those things. So basically, what we are trying to highlight here is that architecture or instruction set architecture is a abstract layer provided to the software designer or compiler designer, which does not change very frequently, and it gives a theoretical description of the machine. And with this theoretical description, I can write programs, I can write my compiler, so that I can assume that, okay, if I follow this kind of or if I assume that these kind of capabilities are there in the hardware, my program will run on that hardware. Now, actually, when you try to design that hardware, that is where the microarchitecture or organization comes in. And there you take decisions based on the several trade-offs, like associated with speed, energy, and cost. And based on that, you take a call, and you figure out like what will be the best implementation for your scenario in the most optimal way. So I try to explain it in a very relatable manner with the mess analogy. You can think of it in any other different ways also. Um, uh, so as the name suggests, architect. So architect tells that, okay, these are the features it will have, and these are the capabilities it will have, but that's a theoretical description. But what actually get manufactured, fabricated, or implemented, that is what is governed by the microarchitecture. So functionally, they will do this. Basically, they has to be similar, because the functionality wise, it should not be different. So if I describe you a mess, so you can visualize something about mess. When you go to it, the reality might be slightly different, but it will perform as a mess. It will provide you all the things which you need in the mess. It may basically impress you very much, blow your mind by its basically, let's say, operations, etc. Or it might disappoint you a bit if there is a long queue and all, but it will still be a mess. So this is what ISA is, and the difference between ISA and microarchitecture is. So I'll take a brief pause here if you have any questions, and if you have also any feedback about the way I described it. It may or may not be very appreciated. But I found it more interesting to explain it in this way, rather than trying to visualize what might be going inside the chip, and what do I mean by ISA, and what do I mean by, let's say, pipeline depth, how they're related, and so on. Okay, I'll pause here so and wait for your questions. No questions? So the difference between ISA and microarchitecture, is it clear?
Yes, sir.
Okay. All right. Thanks. Thanks for the clarification. And so let's quickly move ahead. And so the few other things which we would like to see are, so it's very interesting to know that you can have same architecture or ISA but different microarchitecture. So here we have some examples. So so AMD's Phenom X4, so that's a x86 processor, so it follows the x86 ISA. Also Intel Atom, I'm sure many of you are aware that Intel also attempted towards go into this handheld market through this Atom processor. So this Intel Atom also follows x86 instruction set ISA. But you see their performance, their capabilities are very different. So whereas AMD is a quad core processor, Atom is a single core processor. AMD consumes 125 watt of power, whereas Atom consumes 2 watt of power. AMD can decode 3 instructions basically per cycle per core. So basically it has quad core, so each core can decode 3 instructions per cycle, whereas Atom could decode 2 instructions per cycle per core. It has only 1 core. So you can see the performance difference. The L1 cache size for AMD is 64 KB for instruction and data, both 64 KB. Intel has 32 KB of instruction cache and 24 KB of data cache. And AMD also has 512 KB of L2 cache, and the L2 cache size is same for Intel Atom as well. AMD is an out of order processor. So basically, as I was saying, that if there are independent instructions which are waiting down the line, you can pick them up and execute them faster, execute them before the preceding instructions. So that kind of capability gives you performance, but you have to put lot more additional effort to make sure that you are not doing something which you are not supposed to do. For example, what if there is a branch instruction in between and you are not supposed to execute at all these subsequent instructions? So how do you ensure that? How do you ensure that you are not doing any kind of, let's say, uh, so there are these hazards called write after write hazard. So let's say in one instruction you were updating a variable, and later on in some other instruction you were updating that same variable again. Now when you reorder these instructions, then how do you ensure that this write this update which you were supposed to do later, you are not doing before, and that will result in very erroneous results, etc. But yeah, it gives better performance. The clock speed at which it can work is 2.6 gigahertz, whereas the Intel operates at 1.6 gigahertz. So here is an example of same architecture but different, same ISA but different microarchitecture. Similarly, we can look at uh, different ISA, different microarchitecture, but similar performance. So again, Intel Phenom X4 and IBM PowerPC. So these PowerPC uses power instruction set architecture. It has 8 cores, consumes 200 watt, and it can decode 6 instructions per cycle per core. The cache size is 32 KB for IBM, both instruction and data. L2 cache size is also small, which is 256 KB. This is also an out of order processor, and it can operate at 4.2 4.25 gigahertz. So you see that here the ISs are different, the microarchitectures are different, but performance is similar. Okay. Uh, okay. So these are the few examples which we wanted to discuss. Now, very quickly, going forward, we will see some key features, and basically we will highlight some key features of ISA. and after that we'll move to microarchitecture, let's say pipeline implementation and the superscalar processor, etc. But before that, we will look very quickly about some of the key features of ISA and why they are important. For example, because they determine how your program should be written. So I'm sure many of you have heard or written assembly code where the um, where the ALU always basically by default takes one of the operand from a register called accumulator, and also the result gets stored in the accumulator. So depending on whether your processor basically by default takes one operand from accumulator and stores the result in accumulator, your assembly code or your program will vary. So this is called machine model, and this machine model is part of the ISA. So ISA also tells that what kind of machine model you are following. So the machine model is nothing but where from your operands are coming and where your result is going. So in the next segment of our discussion, we'll be answering this question. And yeah, so before that, let's take a break for 10 minutes or so. So we'll be back at 11:05. But yeah, I'm available for two minutes. So if you have any questions you want to discuss, I'll be happy to answer.
Except for the out of order execution. Um, so who will actually take care so that the results are kind of in place every time? Are we going to discuss more in the sessions? We can pause till then.
The microarchitecture, you mean? Like what? So the correctness of your result. That's what you are.
Yes, sir. Yes, sir. Out of order execution, but there should be some synchronization or some
Yeah.
barriers.
So these are all. See, ISA has given theoretical definition, and ISA has nothing to do with anything more. Now, at microarchitecture level, it's our responsibility to make sure whatever we do, we comply to the ISA which we promised to. So this is the responsibility at the microarchitecture level. So if I do something out of order, it's my responsibility to make sure that I'm not doing something silly. Now, how do we implement this? For that, there are several things. We'll try to cover as much as possible, but may not be everything we'll be able to cover. But broadly, for example, whenever you do something out of order, there is a concept called reorder buffer. So you have a buffer which keeps track of the original sequence at which you were supposed to do things, and that basically you consult that reorder buffer to make sure that all the results which you are generating or you are committing. So before commit, so commit is the state beyond which you can't alter anything. So before committing, that's why you would like to make sure that whatever you are doing, there is no ambiguity and there is no error. Uh, so that can be done by this constructs called reorder buffer. There are basically there are many other things like issue queue. So issue queue is a table again which contains all the instructions that can be issued out of order, which are ready to be issued. And then at the end, the reorder buffer takes care that okay, everything is committed as they were supposed to get committed. So if time permits, we'll talk about it. But yeah, it's pretty vast. So in the superscalar domain, we will talk about these things. Maybe tomorrow or day after, possibly tomorrow.
Okay, sir.
Oh. Okay, so let's come back at 11:05. All right. So welcome back. So any question so far? Yes.
Sir, my question is, sir, when you were showing the difference between AMD Phenom X4 and Intel Atom
Hmm.
within the same architecture but different micro architecture. So my question was like, it was specified they both were having L1 and L2 cache.
Hmm.
So, why is there no L3 cache?
So again, this is a design decision. The introduction of level of caches introduces more complexity, but also provides you better performance. So now you have to take a trade-off, like how many different levels of cache you would like to have, and what is the cost involved in there, and what is the performance gain you will get there. So these are all trade-offs. If you see very recent, basically most of the recent processor with very high performance, they come with 3 level of caches, but not necessarily all processors will have to follow the same. I can have a design without cache also. So we'll talk about memory hierarchies and memory architecture a bit to discuss this further. Uh, but it's not like mandatorily you have to have 3 level of cache. You can have designs with 1 level of cache or even no cache, because at the ISA level, when you decide or at the ISA level, you don't even discuss anything about the memory architecture. You just say that, okay, uh, I should be able to access this much of memory. Now, to basically expedite this excess of memory, you have this L1, L2, L3 caches.
So, but since ISA is basically a decision making, a kind of a theoretical description process. So, at that level, also memory hierarchy is not defined.
No.
So then is it at a physical design stage in microarchitecture level?
Yeah, microarchitecture. So ISA does not specify that how you will access the memory.
Okay.
So L1, L2, L3 is nothing but how you are accessing your memory. You just, from main memory, you keep a copy closer to your processor in the form of L1, L2, and L3, right? So this is the details about how do you access that memory, how make it faster and all these things. So ISA does not talk about it.
And so having a higher higher L3 cache, does it have any impact on performance of the processor?
See, generally, having a large L3, of course, it helps performance because the larger the memory is, the more chance that you will have a hit in the cache. So, whole purpose of having cache is that you speculatively bring in data in your cache with the hope that whatever data you need will be available in your cache. Now, if your size of cache is small, then basically very there is a great chance that you will miss your very frequently whatever you want because you have a small cache. So by having 3 levels of cache, you're basically in the L3 being the largest, you increase the chance of getting the data in your cache. But of course, there is basically physics involved. If you make your cache big, the access time also becomes larger. So L3 being the largest, it will also have access time larger, but of course it's much better than the main memory. So that way having L3 helps only if you can reduce the miss rate by having that L3.
Yeah, thank you, sir.
Okay. 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 So let's resume our discussion. So what we are doing now, we are looking at machine model. So this is called machine model. Uh, So machine model basically specifies or answers this question, where your operands are coming from and where your result is going. So we know that, okay, we have this ALU. ALU will be also basically in our CPU, there will be adjacent to the CPU, there will be memory where from we have to get the data and the instruction. And around the ALU, there will be this, let's say, register files. Now, where from this ALU will get the operands which we need to perform some or execute some instruction. So let's say it needs to add two numbers A and B. Now, and then it has to store that result into C. So depending on the different varieties of where this data can come from, basically A and B can come from, you have different machine models, and these machine models are also described in your instruction set architecture. So what could be the simplest machine model? One very simple machine model is called stack-based machine model. So what is this stack-based machine model? So again, stack is a software construct. So basically any part of memory I can declare as stack. So stack memory, the advantage is that you don't need very elaborate mechanism to find data from stack, because stack by design is like this. So as the name suggests, it's basically stacks. So you put your data one top of another, just like a stack of books. So you start putting data one top of another, and if you want to read or access data, so you have to access from the top itself. Okay. So just like you create a stack of books, and then when you take out books, you have to take one from the top, and then only you can take the next one, and so on. Now one machine model says that, okay, both your operands will be the first two elements of the stack. Okay, so let's say this is your defined, this part of the memory is defined as your stack. So the first two elements of the stacks are your two operands, and the result is again stored back at the top of the stack. Okay. If we want to visualize it like this, let's say I want to add A and B. So, and this is my, so basically stack of books. So A is here, B is here. So by default, when I say add, the ALU will take these two operands and the result will be stored in this place. In place of B, the result will be stored. Okay. Now, what are the advantages? The advantage is that you do not have to explicitly mention your operands. So just to give you this, okay, so okay, we'll come to that. So basically in this case, let's say if I want to write the code to do this operation, so what I'll do, I'll just write that push A. So push A will put A at the top of the stack. Then I'll write push B. So this will put B next to, basically it will, first A will be put, then B will be put. Now if I just write add, then the top two elements of stack will be by default added, and the result will be stored at the top of the stack. Okay, so I have to just write add. I don't have to explicitly say that add A and B and store it in C. So now I want the result in C. So what I'll do, I'll just pop. So pop means I'll be reading the top content and I'll be storing it in C. So pop C. So in this machine model, you see that you do not have to explicitly mention any of the operands. So this looks very nice. And it's very simple also. So if you really want to design a very simple processor, this can be one machine model which can be followed. But the disadvantage is that every time you have to do some arithmetic operation, you have to first push the operands at the top of the stack and then do this operation. Now, if you need to, let's say, repeatedly use some variable like b, so you have to repeatedly push and pop this variable depending on what you want to do. So that is one machine model. Similarly, the other machine model is called accumulator based machine model. I'm sure many of the microcontrollers, if you have used, it follows this machine model, accumulator based machine model. So here, one of the operand which the ALU works with is a register, specific register called accumulator. And the result is also stored in accumulator. So here you see that this is our ALU. One operand is coming from an accumulator, the other operand is coming directly from memory, and then the result is stored in accumulator. So if I want to write this same thing, like our objective is to do this, C should be equal to A plus B. So what I should have to do, I have to first store or move the value of A to the accumulator. So let's say move A. So by move A, the value of accumulator, value of A will be moved to accumulator, because by default one of the operand is with your accumulator, and then I will just write add B, because A is already in accumulator. The content of B, which is in memory, will be added, and the result will be stored automatically into C. So then I have to just write basically move the value of accumulator to C. So that will be that is how my code will look like. We will see that. Similarly, if I have a register memory kind of machine model, so in this machine model, the one of the operand is coming from a register, the other operand is coming from memory, and the result is stored in another register. So now here you can have either 2 or 3 explicitly mentioned operand, depending on whether the result is stored in the same register. So if your result gets stored in the same register, then you do not have to explicitly mention the destination register. But if it is not so, then you have to explicitly mention the destination register. And then the fourth model is called register model, which is more popular. So here all the operands are coming from register, and the result is also stored in register. So we will quickly look at how okay, so the named operands in each of the cases. In case of stack, we have seen that there is no named operand, because top of the stack 2 elements are by default your operands. In case of accumulator, you have to explicitly name one of the operand, because other operand is always accumulator. In case of register memory, it can be 2 or 3. 3 if all of them are different. So basically this register for as one of the operand, this memory as one of the operand, and the result is stored in this register. The other, so in this case there will be 3. The other option could be you have this as one of the inputs, and the result is also stored in this only. So in that case, you don't have to explicitly mention the destination register. That's how it becomes 2. And in case of 3, basically in case of register case also same thing. You can have 3 different registers for your 2 sources and destination, or one of the source could be your by default destination. In that case, you need 2 explicitly mentioned operands or named operands. So we will quickly look at how our assembly code will vary if we want to do this operation in these 3 machine models. So you see that this is how the different instructions, different code segments will look like based on which machine model you are following. So in case of stack, it's push A, push B, then add and pop C. In case of accumulator, load your basically value of A into the accumulator, add B, and then store the value of accumulator to the variable C. In case of register memory, so you load the value of A to a register R1, then you basically add R1 and B and store that result into R3, and then you store the value of R, basically the value of R3 in C. The fourth one, you load register A with R1, B with R2, then add R1 and R2 and store it in R3. Basically, the destination is R3, and then store the content of R3 to C. So this is how your assembly code will vary depending on the machine model you follow. So that's why it's important to specify the machine model in the ISA itself, so that as a programmer I know whether it's an accumulator based system, whether it's a register system, or a stack based system or register memory system. Now intuitively, can you guys tell that which one of these machine model is more efficient, or basically is best in most of the cases?
So register model.
Why?
So because we'll not be dealing with the memory, we can directly manipulate the data from the register itself.
Yeah, true. Because so by looking at this snippet of code, it might look like, oh, register model, the code length looks largest and so on. But the advantage, as Archit has pointed out already, is that it's not like the variables A and B you are using only once. You very likely will be using them multiple times. So once they are stored in R1 and R2, then for every time you need to use A and B, you have to just use R1 and R2, and it will be much more efficient. If you look at the stack based model, so every time you have to use A and B, you have to again push and pop them accordingly. So that becomes tedious. Similarly, the accumulator based system, it's simple, but every time you have to do this additional loading, or one of the operands should be loaded into the accumulator, and then again the result has to be stored somewhere. So these kind of additional steps are there in the accumulator based system, but definitely it's much simpler. That's why most of the microcontroller, it uses accumulator based machine model. Because these registers, if you have, let's say, 16 general purpose register, you have to have addressing mechanism to address those registers, to find out what is stored there and so on. So it's more hardware is needed, but of course more efficient than the register model. And most of the processors, ISAs, you will encounter, they use this register model if you are dealing with general purpose processors. Okay, so RISC-V, ARM, MIPS, all of them use register model. Any quick question before we move ahead?
So I would also like to add, like in register memory model, sir, I think getting the memory address is also challenge, because you have to access the memory via address and then allocate the data to it.
Yeah. So of course it requires additional steps, time, etc. Yeah. But it also gives some flexibility. So by the way, x86 is a register memory model.
Okay, sir.
So we might not realize this, but yeah, this is so. The advantage here is that one of the operand can be directly memory, so which gives you a lot of flexibility as well. But of course, as pointed out by Archit, accessing the memory is a lengthy process. But if your memory which you are looking for is available in your cache and you can access it quickly, then this problem can be addressed to a great extent.
So then, can we say like in modern processor which are being manufactured today nowadays, it is kind of like a hybrid system in a machine model being implemented between register model and register memory.
No, no, it's not hybrid. They are very clear. So x86 is a register memory model. Most of the RISC processor are register model. So at
Okay,
the
sir.
ISA level, you have to be very clearly defining like what is your machine model. It's not hybrid.
Okay, sir.
Oh, and by the way, in x86, the explicitly mentioned operand is basically 2. So the first operand is always the destination. Okay, so basically if I want to write this add instruction in x86, it will be like add. Then I have to just tell R1 and B, because the destination, the result will be always stored in R1. And yeah. Okay, so let me go ahead. Then so we one important element of instruction set architecture we have seen, which was machine model. Then there are different instruction types. So for example, here it is mentioned as classes of instruction. So there will be instructions which are dealing with transferring of data. So these are MIPS instructions. So you can basically look it up if you are interested. For example, LD stands for load, ST stands for store, uh, uh, MTC is basically move from or move to. Um, so these kind of instructions, which are data transfer related. ALU does all the arithmetic operations, arithmetic and logic operations. The branch related instructions or control flow instructions like branch if equal to 0, jump to a register, a jump at a level, and all these things. Then floating point operations, like whenever you need to add do floating point operations, you will have instructions like add.d, sub.s, etc. Um, then there are multimedia instructions, like these are basically single instructions, multiple data. So same thing you need to do on multiple data. So instead of writing them again and again, you can write this SIMD instructions. Then there are some string instructions, like this is an x86 instruction, wrap move SB. So basically here copy one string to another string. So that can be done using a single instruction. So you see that CISC is very different, where complicated things are done on using a single instruction, whereas in case of RISC you do only the basic stuff. um, yeah, so so these are also specified at the ISA level. The addressing mode, so how do you specify your different addresses? So the different addressing modes are listed here, but most commonly used are the displacement kind of addressing mode, where basically you mention your address like a base offset. So in this case, if you look at the displacement thing, so this is as if your base address of that okay uh, okay, so basically this is the base offset, base register, and then you use this offset to identify which element in that particular let's say array you want to read. And this is one of the popular addressing modes, because you generally try to read elements in your array, and updating this offset value is much easier. So let's say now you are looking at this element, and next you want to read the next element. So basically you just update or increment this offset value, and that will point to the next element of the array, and so on. So there are different different ways your address can be specified. Some of them are specified through register. So basically the content of the register specify the address. Um, Register indirect, where basically the content of this R1 is point to a memory, and that is the content of that memory is basically what you are looking for. So yeah, these are relatively, basically you can just look at them and you should be able to understand what it is doing. But the key point to take away is that these different addressing modes are also specified, that what kind of addressing mode your ISA allows. All these things are specified in your instruction set architecture. The data types, these are also again very important things which are specified in the ISA. For example, whether you can deal with binary integer, binary BCDs, whether you will be able to deal with floating point numbers. So how do you deal with floating point numbers? Do you follow the IEEE 754 format? So in IEEE 754 format, I hope many of you know this, the any number is represented like this: -1 raised to the power sign bit. Then you have your number is represented like 1 plus m, um, and then 2 to the power x, right? So here m is the mantissa, which lies between 0 to 1, and x is the exponent, which is for single precision or 32-bit floating point numbers. You specify, I think, 8 bits for the exponent, and you specify 23 bits for your yeah, 8 bits for exponent and 23 bits for mantissa. So the IEEE 754 format looks like this. For a 32-bit floating point number, you will have one sign bit, then 8 bits will be representing the exponent, and then the 23 bits will be representing the mantissa. Okay. And you can represent any number using this IEEE 754 format. There are other floating point standards, but yeah, 754 is the most popular one. Your ISA should specify how you handle these floating point numbers, etc. The width of your numbers, for example, binary integers, whether they are 8-bit, 16-bit, 32-bit, or 64-bit. Similarly, floating point numbers, the address width, all these things are specified at the ISA level. Now, how do you basically encode your instructions? Should they have fixed length for all the instructions, or basically fixed width of all the instructions, or they should have variable width? So this also is determined by the ISA. If every instruction is of the same width, then it's much easy to decode. Basically, okay, we can look at one example. Let's say I have my 32-bit instruction. Okay, and let's hypothetically think about that the ISA I'm looking at, it has let's say 25 instructions. So I'm building a processor, and let's say I'm also building the ISA for that processor. So I identify that I will be dealing with 25 instructions. So to uniquely represent each of these instructions, I'll need at least how many bits? Are everyone? 5, right? Yeah. So I need 5 bits. So in my 32-bit instruction, so I'm trying to basically find out what my instruction will look like. So in my instruction, 5 bits will be going for opcode. So that I can identify each of these instructions differently. Then I'll have, let's say, 2 source registers and 1 destination register. If all my operands are specified through register. So let's say I have 16-bit registers, 16 general purpose registers. So to identify each of the register uniquely, again, I need 4 bits. So so basically, let's say this is my destination register, so it will take 4 bits. I'll have 2 source registers, RS1 and RS2. They will also take 4 bits. So basically, pretty much, if I'm not dealing with immediate value, so basically directly I'm dealing with, let's say, numbers, then I can encode my instruction using this 12 plus 5, 17 bits. But you will see that most of to do most of the thing, you need to also deal with immediate values, and for that you will need some additional bits. So what I'm trying to say is basically I can have fixed fields in my 32-bit for each of these let's say destination register field, source register field, first source, second source, and immediate value, etc. Now, if I have this thing fixed for all the instruction, then my hardware becomes much simpler, because I know that, okay, to identify which instruction it is, I have to just read first 5 bits. That will tell me what instruction it is, and accordingly I'll generate appropriate control signals. I'll know where from my operands are coming, basically whether it's the 2 source registers which I need to read, and so on. So this is what most of the RISC ISAs follow. So whether it's MIPS, PowerPC, Spark, ARM, RISC-V, all of them basically use this fixed length instruction, fixed or fixed width instruction. This is the way they encode their ISA. Now 32-bit means basically 4 bytes. So that's basically MIPS use instructions of length or width 4 bytes. Now there are ISAs which allow variable length, variable width instructions. There are advantages also. Let's say I'm trying to design an instruction and ISA, and in that ISA I know that the kind of application this ISA will be dealing with, there one specific instruction is very frequently used. Let's say you are designing a machine learning processor, or basically a processor which will be doing lot of multiply and accumulate kind of operation. So every let's say 90% of the time it will be doing multiply and accumulate. So in that case, you might decide to reduce the length of that frequently used instruction and encode it in such a way that by reading 3 bits, you will know that, oh, it's again the multiply and accumulate. So do this steps. So that basically makes your system perform better, more optimized. But for 10% of the time, when you do other things, maybe you have to spend more time, because now you have variability. Your instruction, the opcode can be here. Basically, not necessarily these 5 bits. It can be contained in first 3 bits, or rest of the things are very different, and so on. So you need to have additional intelligence to know what is the width of your instruction, and accordingly you take a call. It takes less space in memory and cache, because as I said, like the very frequently used instruction you can reduce in width, and that saves your instruction total code size, etc. But that also adds additional overheads, because now your hardware should be every time, it's not by default that I read these 5 bits and I will get the output. So you have to have some additional checks to identify them. So most of the CISC architectures, complex instruction set architecture, compute architectures like IBM 360, x86, Motorola 668K, VAX, they use these kind of variable weight instructions. There are something intermediate also. For example, there is a there is something called thumb by ARM. So thumb, as the name suggests, so ARM is the full length 32-bit instruction. Thumb is a truncated version of that, which only has 16 bits. So it's not randomly variable. It basically it can be a combination of ARM and thumb. So basically either 32-bit or 16-bit. Similarly, MIPS also has a MIPS 16 version. Um, um, so these are something in between. Tries to, so these ISS tries to take advantage of both the world and try to make it more efficient. The very long instruction word like VLIW kind of instruction, they basically put multiple instruction and together to create a bundle, and then basically all the instruction or multiple instruction which can go parallelly, they put them together and create a bundle, and that results in your instruction weight to be pretty long. So we'll talk about VLIW if time permits. So all these things are properties of ISA. Okay, so all these specifications are from ISA. So this is one example of x86 instruction encoding. Again, I'll leave it to you guys to look at closely. You see that since it's variable length instruction, you see each of these fields can take a variable number of bytes to be represented, and each instruction can be from 1 byte to 18 bytes. So the variations are that much. So some of the real world instruction set architectures, just to give you the heads up about, or basically a glimpse of different ISAs and what they are used for and what is specified in those ISAs is listed here. So alpha is a ISA which is a register ISA. All the three operands are explicitly mentioned. Its data size is 64-bit. General purpose registers are 32, and address size is 64-bit, and typically used for workstation kind of application. ARM is again register machine model. Three operands explicitly mentioned. Data size could be 32 or 64. General purpose registers 16, and address size also can be 32 or 64. Typically used for cell phone embedded system, but now you see ARM is even used in supercomputers. MIPS again register, pretty much similar to ARM, only difference is the general purpose register is number of general purpose register is 32 instead of 16. Spark is another ISA, pretty much again same, number of general purpose register varies from 24 to 32 and primarily used for workstation. TIC 6000 again register, and yeah, 32 general purpose register, 32-bit and DSP applications. IBM 360. So IBM 360 and x86 are quite similar. Both of them are register memory. Two operands are explicitly mentioned. One of them comes from memory, and the register is by default the destination for the result. Data size for IBM 360 is 32-bit, whereas for x86 it can vary from 8 to 64-bit. Register numbers are also for x86 varying from 4 to 24, and address size can also vary from 16, 32 or 64. And x86 is primarily used for personal computer, whereas IBM 360 is primarily used for mainframe kind of computers. Then there is VAX, which is a completely memory machine model. All three operands are explicitly mentioned, and three are coming from memory. And data size is 32-bit. General purpose registers are 16. Address size is also 32-bit, and it is one of the very old computer specs which was used in mini computers. Motorola 6800, it's an accumulator based machine model. So here one of the operand is explicitly mentioned, another operand comes from memory, another one or two operand comes from memory. Data size is 8-bit, no general purpose register, and address size is 16-bit, primarily used for microcontrollers. All right. So these are few real world instruction sets. I think, yeah. So, okay. So why this different diversity in the ISAs? Because of several reasons, the way things evolved. Ideally, what you want, let's say I want to design a processor. Let's all of us sit together and say that, okay, by end of this course, we will have a ISA for our processor. And with this aim, if we sit together and build a processor, and we have some idea about the application in mind, then we can think of that, okay, what kind of instructions I'll need. And then we can look at, okay, for each of these instructions, how this microarchitecture will look like. And if we identify that, okay, for let's say one instruction, the microarchitecture is becoming very complicated. So we'll figure out, like, can I live without that instruction? Also, like, depending on my constraints, I'll find out, like, okay, what all I can put in together. And based on that, I will decide about what ISA I want. So for example, let's say floating point arithmetic, if I want, then I know that I have to spend lot of additional hardware, overhead, etc. Now, the question will be, can the application I'm targeting uh, uh, can it be possible that without floating point I'll be able to manage? Now, if we all decide that, okay, without floating point we should be able to manage the accuracy, the lack of accuracy what we'll be encountering, this is okay, as long because we are saving lot on in terms of like hardware cost, etc. So these kind of design decisions result in newer ISA, because not all, basically off the shelf ISA may not be able to give me all the optimization which I wanted. So you try to reduce your instruction set computer, and you keep on removing instructions until the whole thing fits into your budget, into your die, and so on. So that's how the variations in ISA came in from some extent, from one level. Then the introduction of multi-core and many-core resulted in, let's say, the basically it became very clear that we have to focus on multi-threading, etc. You have to highlight those capabilities, and because of that, uh, uh, you can think of newer ISAs which will be exploiting the different threads much more efficiently. And also applications like, let's say, machine learning or DSP, there you need to do things, specific things very frequently. For example, maybe some video encoding, video decoding, or lot of data crunching. So based on that, also your microarchitecture might evolve. Also compiler technology, because some of the things which compiler could not do earlier, now because of the advancements can be done at the compiler level. So the previous restrictions are no longer there, so accordingly you can update your ISA. But as we have mentioned earlier, the ISAs do not get updated very frequently. They are very slow because of all the legacy reasons. You don't want a new computer which can't run, let's say, some old files or old programs. Then the acceptability of that new computer will be very, very limited. So to maintain all this backward compatibility, you will not change ISA drastically, but there are diversity in the ISA, and those diversity come primarily because of all these reasons. All right. Okay. So this is what we wanted to discuss about ISA primarily, and I can pause for 1 minute if you have any question, and then we will move into the microarchitecture. Okay. Now, before we move to microarchitecture, we have to understand what we have seen. So we have said that, okay, I theoretically describe that, okay, this is how my machine will be. It can do these things. These are the different instructions it can handle. It can take 32-bit data as input. It can address this much memory. The machine model it will be following is this, and so on. So this theoretical description we have got from our discussion so far. Now, let's say through this exercise, we have also come up with some hypothetical ISA. The hypothetical ISA has 20 instruction, and it is a 32-bit processor, and the machine model will be register machine model. And that's about it. So let's say we call it the ISA of IIIT Delhi. So maybe just name it as IIIT Delhi 32-bit ISA. Now, the next thing we need to do is basically we need to build a hardware which will be compatible with that ISA. So how do we build that hardware? So that's the exercise we will be doing now. Now, let's say I don't have much idea about how to build this computer, and I start in a very crude manner. The crude manner which I opted for is like this. I identify 20 instructions which the ISA supports. So what I can do, let's I list out all these 20 instructions. Okay, so these are my 20 instructions. For each of the instruction, I take one instruction at a time. I build a hardware to make sure that I can execute this task, and I put that hardware somewhere here, and I keep on doing this for each of the instructions. So I have 20 such instructions, so I'll have 20 such blocks. Now somewhere here I identify that, okay, which instruction I need to execute. From this 20 box, I select one of the box depending on which instruction it is, and then I collect the result and give it back to my processor. Is it a viable way of designing my hardware? Do you see any issue in this way of designing hardware? I need to get some response.
So it is not viable because we need more area for, and we need different, the same architecture for different instructions.
Yeah, yeah. So though functionally possibly it will work, but it's a very unoptimized way of doing things, right? Because every time I will be, let's say, out of this 20 instructions, there will be many instructions which will be using the ALU, but for each instruction I'll be building a separate ALU. So it's definitely not a very good way of designing your processor. So the more reasonable way of building this processor is to basically see whether I can develop some generic hardware and then multiplex those generic hardwares to execute all my 20 instructions. Um, uh, so that will be a more viable way. Now, so what we can do, we can each instruction, whatever task it is doing, we can divide the task into multiple subtasks and uh, see how this will just give me a moment. Hello. Yeah, sorry about that interruption. Yeah, so what we can do for each instruction, we can identify some of the, basically we can divide the whole task into multiple subtasks and then try to basically execute them or reuse some of these modules as much as possible. So one concept which we need to learn before we move ahead is called pipelining. And pipelining as a concept, I'm sure you might have some sense. So generally in pipeline, what happens? Let's say you have look at the car assembly line. So in car assembly line, let's simplify the manufacturing of a car process into 5 steps. So in the first step, let's say the car just bare body comes in. In the second step, or bare body is made. The second step, let's say all the painting and all these things are done. Third step, all the electronics are fitted in. Fourth step, let's say engine is fitted in and all the seats, etc. are put in. And fifth step, it's basically the fine tuning of or checking that everything is working fine. Now, if you look at the conveyor belt which is carrying these cars, so as soon as the car from the first stage moves to the second stage, a new car occupies that first stage, and the subsequent cars move forward. So this is the basic concept of pipeline, and here we have shown in an ideal manner how this pipeline is generally implemented. So you have several stages in the pipeline. All the objects, or whether it's car or whether it's let's say some other thing which need to be manufactured through this process, all of them go through the same stages. So you can't skip any of the stages. Also, you do not share any resource between any two stages, because if you share any resource, then if that resource is not available, then you will be stuck and you can't move forward. Also, there are these assumptions here is that the propagation delay through all the pipeline stages is equal. So basically, it takes same amount of time to get the work done in first stage and second stage and third stage and fourth stage. So let's say each of these stage takes 10 seconds to execute the work. Now, if one stage takes, let's say instead of 10 seconds, it takes 8 seconds, then also it will wait for 10 seconds before it moves to the next stage, because of the mechanism of this basically, let's say, let me do. So these are kind of gates or sequencing elements. So these gates open periodically. Every 10 seconds, basically whatever is currently input, it will become basically it will be available at the output after this 10 seconds. So basically, as if every 10 seconds these gates open up, so the new input is allowed to go in, and then this gate close, and it remains closed for next 10 seconds. By that time, the data which has entered here goes through this stage, and all the operations are done, and you have a new data available before this window of 10 seconds ends. So in the when the next stage comes, basically whenever the next occurrence happens and the gates open, the result which is available now, it moves to the next stage. So think about it as basically your car. So the car at the first stage is waiting here. As soon as the gate opens, it moves to here, and then it takes 10 seconds to get ready for the next stage. So by 10 seconds it reaches here, and after 10 seconds, as the gate opens, the same car which was here earlier, it has moved here. Now it will move here, and so on. So subsequently it will move to the subsequent stages, and the new cars will follow it. So let me know if this makes sense. Otherwise, I am not spending too much time in explaining this. But if you need further explanation or if you have doubts, I'll be happy to clarify this. Now, the assumption here is that since the gates open at the same time, so every stage has to take same amount of time. Even if it is taking less time, it will be waiting, doing nothing. But if any stage takes more time, then let's say this stage, instead of 10 seconds, it takes 11 seconds to prepare the car. Now, when the next clock cycle comes, or the next time when the gates open, this car is not ready because it's only 10 seconds and it takes 11 seconds to be ready. So that will create a problem, because a new car will enter here, but this car has not gone out of this stage. So that will create a problem. So that's why the slowest stage, if the slowest stage is, let's say, 11 seconds, then you have to decide that, okay, every 11 second or 11 second plus some overhead time, only I'll be opening the gate. You can't operate or open the gate before that. So the slowest stage will determine the time at which you can regulate this gate. And so these are the characteristics of your ideal pipeline. Scheduling of a transaction entering to the pipeline is not affected by the transaction in other stages. So basically, whatever is happening here has no impact on this. And every time this gets open, every stage, so data from one stage to next stage will move, and this will be happening for all the stages.
So it means if any stage has a maximum time, so we need to open the gate at the more than that time, right?
Yeah. So for example, let's say this takes 8 seconds, this takes 15 seconds. Now the frequency at which I will open this gate, means all these gates open at the same time.
Yeah.
So the frequency at which I will be opening this gate will be 15 seconds. Okay, so because this stage is taking 15 seconds to prepare the data. So in basically in our common language, we call it the critical path. So critical path is the path which is taking the most amount of time. And that determines at what clock frequency you can operate this. This is nothing but your resistor transfer logic, right? Resistor transfer logic circuit. Now, if you want to make it faster, then you have to look in detail and deeply into this critical path and see whether I can improve this delay further. If I can improve it further, then I can clock it better. Okay.
Yeah.
Now, all these conditions which we have discussed so far, these are generally hold true for industry assembly lines like car assembly line, etc. But when we talk about instructions, our instructions are dependent. They are not independent. For example, in like maybe some instruction, I'll be updating a variable, and then in the subsequent instruction, I'll be using that variable. So that concept of completely independent and all these things are not fully applicable here. But we do want to use pipeline. Why we do want to use pipeline? Okay.
To speed up the process.
Yeah, to speed up the process, because okay, so another crude example could be same mess. In the mess you can have 5 items put together, put in same place. So one student goes in, takes all the 5 items, goes out, so it takes, let's say, a certain amount of time. Whereas if you divide it into multiple stages and students can parallelly take different items and move forward, that will be much more faster. So that will give you better performance. So that's why we want to introduce pipeline. So remember our goal, we want to, we have a bunch of instruction from our ISA. Now we are trying to build the hardware which will execute those instructions. So first step, we said that, okay, we will break this execution down into multiple stages. And now we also want to basically pipeline this execution. So basically, let's say each instruction is divided into 4 or 5 stages, and then we make these stages independent enough so that, let's say, stage 2 is dealing with instruction 1, stage 1 is dealing with instruction 2, and so on. So different instructions are getting executed at different stages, and since they are isolated from each other, independent from each other, so ideally I should be able to do it. So let's go ahead and see how we can do that. Okay. This is the microarchitecture of a unpipelined MIPS processor. So don't get overwhelmed. I'm not going to go into too much detail of it. So typically, what all is getting done, let's try to, at a very top level, try to understand this. So for any instruction, what are the things I have to do? I have to first figure out what is the instruction I'll be executing now. So for that, I have to read my instruction memory and find out what is that 32-bit instruction. Because remember, though we are talking about MIPS here, but let's forget about MIPS and we say keep on our discussing about our ISA, the 32-bit ISA which we want to design. So to execute a program in our ISA, we will be reading 32-bit instructions from our instruction memory. So the first step is basically to read what is there in the instruction memory. What is the first instruction? So to get to that first instruction, okay, let me go back to the previous slide and explain it from. So the first stage, let's say, is instruction fetch. So I have to fetch this instruction from my instruction memory. Now, how do I fetch instruction from instruction memory? I have to have some kind of address to know that, okay, this is the instruction which I need to fetch. Now, generally, this address is stored in a register called program counter, PC. Okay. So I'll be, in this stage, first stage, what I'll do, I'll read my PC. So what is the address stored in PC? And after reading that address, I'll go to my instruction memory. I'll find out what is the 32-bit instruction which is stored in my instruction memory. Bring it out. Basically, I'll read or fetch my instruction that I need to execute at this point. Now, in this stage, I will also need to do something else. Well, so we have fetched the instruction, but I also need to update my program counter so that next time when the I want to read the next instruction, I can read the next instruction, not the same instruction. So what I'll do, I'll fetch instruction in stage 1, and also I'll update my PC to point to the next instruction. So if there is no branch or any other thing like that, let's say assuming that the next instruction is the immediate next instruction which I have fetched right now, then generally it will be PC will be updated by PC plus. Remember that we said that our instruction width is 4 bytes, and our address, basically we have a memory which is byte addressable. So basically every byte I can address separately, but since my instruction is 32-bit long or 4 byte, so to get the next instruction I have to add my program counter, or I have to increment my program counter by 4 units, because that will point to the next instruction. I hope this makes sense. So if I increment my program counter by 4, that will point to the next instruction. So this is the task I'll be doing in stage 1. In stage 2, now I have brought the instruction. I know what is the instruction. So in stage 2, actually I'll look at the opcode, and using that opcode I'll generate different kind of control signals that are required. For example, if it is a let's say if it is a add instruction, then I have to tell my ALU that do addition operation. If it is a, let's say, multiply operation, then I have to again tell the ALU that it's a multiply, not add. So depending on my opcode, so basically I have this 5-bit opcode, right? So I will, depending on that 5-bit, I will generate different control signals which will be required for different stages. That will be done in this second stage. So let's say this stage we called as decode stage. So in this stage, I decode what is those 5 bits of operand saying. I generate all the related control signals. The next thing I need to do, I also figure out where my operands are coming from. So for example, let's say the 32-bit instruction, it had this 5 bits of code. Then my, let's say, the destination register and the source register 1 and source register 2. Now in this decode stage, what I'll do, because destination I don't have to do anything. Once I get the result, I'll store the result in destination. Now I have to find out what are the values of RS, my source register 1 and source register 2. So I have this register file. So I'll give these addresses to my register file so that I can read the content of the source register 1 and source register 2, and these contents are given to the next stage. What is the next stage? Next stage is the execute stage. In the execute stage, what we do? We take the operands, and depending on the control signals, we figure out, okay, I need to do this operation. So the ALU is informed that, okay, these are the 2 operands, and do this operation on these 2 operands. So after the execution, so basically in the decode stage, we what all we do, we generate all the control signals, we read these operands and basically supply them to the next stage, which is the execution stage. In the execution stage, we take the operands, values of the operands, and then do the appropriate operation, and the result is so we prepare the result. Now so this is our execute stage. Now there are some instructions which need to talk to memory. So the next stage is memory. So in this stage, we basically we get, let's say if it is a load, so what kind of memory instructions we generally deal with? These are load and store instructions. So in case of load, we need to load the value from memory to some register. So generally from the earlier stages, either from the decode stage or from the execution stage, we get the address from where the loading need to be done. So let's say the address is given in the form of base offset. So there you have to add the base with the offset. So that kind of operations are done in the ALU again. Any kind of arithmetic operations done in the ALU. So the ALU gives you the address. You in the memory stage, you read that address of the memory and bring that content out if it is a load, right? Okay, so I have to load this value. So I read the memory address, I bring that content out as part of the memory stage. If it is a store address, that store command, then in that case, again, I will be needing the address where I need to store the value. So I will have the value, and that value will be stored in that particular address in the memory stage. The next stage is called write back. So in this stage, let's say I have an instruction that load this value from memory to this particular register. So I have read the content of memory. The content is available now. In the write back stage, now I will update that content into that particular register. So basically in the write back stage, we again update our register files, general purpose register files. So these are the 5 stages in which we can divide our instruction execution into. And of course, I have ignored many of the details. For example, what happens when there is a branch instruction? How do your program counter gets updated? At what stage it gets updated, and so on. Similarly, if it is let's say a compare instruction, so where things get updated, and so if time permits, we'll go into that. But broadly, what we have done, we have divided the task of executing or evaluating one instruction into 5 stages, namely instruction fetch, decode, execute, memory, and write back. All right. Now, if I look at this figure, the microarchitecture, which is unpipelined, so you will see that this is precisely the part which is doing instruction fetch. So see, this is your instruction memory. Program counter gives you the address from where you will get the instruction. And then this program counter is incremented by +4, or if there is a branch instruction, then this program counter need to be updated separately. So these are the different possibilities by which the program counter can update it. So these are further details which we can for now ignore. And then depending on whether the program counter has to be incremented by 4 or some branch instruction will decide what will be the program counter value, you will be updating your PC accordingly. So this is your instruction fetch stage. Instruction decode, basically here the control part is not given, but let's say this is your instruction. You got your 32-bit instruction, you separate out the opcode. From that opcode, you generate all the control signals. Now, this is your register file. So you read your basically 2 source registers, and those 2 source registers are provided to your basically ALU for the execution stage. Again, I am ignoring many of the things here. You see that there is an immediate mentioned here. So basically, if you are doing, if you are dealing with directly values, for example, let's say I want to load the value 5 in, or I want to add the value 5 to a register content. So that 5 will be communicated as an immediate. So yeah, so that we are ignoring at this point. So the decode stage is this. It gives me the operands to the execution stage. So this is execution stage, which basically executes the operation. All the control signals will determine whether it is what kind of operation it will be doing. So we are done with the execution. Then the results are ready. Now, if you need to do load and store, then your data memory comes in picture, right? So if you need to load, then you access the data memory. Similarly, if you store, you store the data in the data memory in the memory stage. And then the last is the write back stage, where you, for example, you have loaded some value from memory, and that value should be written to a register file. So that is done in this stage. So your register file is same. So the same register file you are accessing in the decode stage, and same register file you are updating in the write back stage. Similarly, let's say you want to, you did some operation like this. So let's say A equals B plus C. Now A is stored in, A is represented in register 3, right? So what you will get after the execution stage, you will get the result B plus C, which is available as a ALU result output. Now this value need to be stored in R3. So that update of R3 will happen in the write back stage. In the write back stage, you will take the result, and that result will get updated into the R3 of our register file. Okay, so these are the 5 stages, and these are the simplified version of these 5 stages. We have got rid of most of the clutters there, and now we are saying that we would introduce pipeline in this simplified data path or unpipelined data path. So what we can do, we can, so how do we pipeline, introduce pipeline? So we basically have to have sequencing elements, because otherwise these are electrical wirings, right? So if I make any changes here, let's say I make any changes in the address, then a new data will come out, and that new data again is connected through wire, so it will change everything in the subsequent stages. So if I do not have any kind of sequencing elements or any kind of gates which do not allow data to move freely, or data only moves when I want the data to move, that can be only implemented if you have some kind of sequencing element. Without that, you only can deal with one instruction at a time. So basically, you fetch one instruction, you do all the things, all the 5 stages you go through, and once you are done, then only you allow the next instruction to be fetched, because otherwise there is nothing which is controlling this flow. So to introduce something which will control this flow, we have to have these sequencing elements, which are nothing but flip-flops. So these flip-flops are, you can assume that, okay, very simple D-type flip-flops, where input is your D, output is Q, and if this is a clock, this is the clock, and it's a positive edge triggered flip-flop. Now what happens if whenever the positive edge comes, whatever is the input, that is latched at the output, and it remains like this till the next positive edge clock comes. So it will it allows as if the input to go to the output at the moment when the positive edge came, and it holds on to that value till the next positive edge comes. So your objective will be to get the work done which is supposed to be done in this stage or in any of the stages before the positive edge of the clock comes. So every flip-flop is connected to the same clock, and the moment the clock edge comes, you allow the result of this stage to go to the next stage, and the next stage will be working on this data and be ready with the result before the next positive edge of the clock comes, and you keep on doing it like this. Now what determines what will be the clock frequency at which you can operate it? That is determined by the maximum time taken by the different stages. So this is the instruction fetch stage, the decode or register fetch stage, the execution phase, the time delay of execution phase, the time delay of memory phase, and time delay of write back phase. Now, depending on which stage takes the most amount of time, that will determine the clock frequency, time period of the clock. Okay, so, and that will be the critical path. Yeah. Now, not only this data movement should be pipelined, your control signal also need to be pipelined. So generally you generate all the control signals in this stage. Okay, so you will generate, so let's say the instruction 1 is in the code stage, so you will generate the control signal corresponding to instruction 1 at this stage. Now when instruction 1 moves to the execute stage, it has to receive the corresponding control signal, then only it will be able to execute things properly. Similarly, when it reaches to the memory stage, it has to have its own control signal, appropriate control signal. So it's not only the data which you are pipelining, your control signals also need to be pipelined. So basically all these control signals will be pipelined as well, so that the moment the instruction 1 moves here, the appropriate control signal for instruction 1 also moves here, appropriate controls. Okay, so this will look something like this. Yeah. Okay. So yeah, your control should be also pipeline. So yeah, I'll stop here today, and we will start discussing from here. We will talk about performance. How do you calculate or evaluate performance? So CPI is one of the metric which is used for evaluating processor performance, and this is cycles per instruction. We'll talk about it in the next class. So yeah, your control signal and the data both need to be pipelined to achieve a CPI of because if your control is not pipelined, then if your though your data is pipelined, but as the instruction moves, you will not get appropriate control signals, and that there will be error in execution. So that's why you have to have control signals also pipelined. All right, so I'll pause here and I'll basically wait for your questions if you have it. Questions or any feedback, like if things are becoming very easy, intuitive, I should pace up, because I have a lot of things to discuss, and depending on where you are, if these things are making sense, do let me know whether I can pace things up a bit, or I need to explain or spend more time on some of the things. So I'm leaving it to you, because in these online settings, I can't see your face, so I can't make out whether how much is getting absorbed. So you guys have to tell me what is working, what is not working, and accordingly I'll maybe calibrate the pace. Okay, so Glenn, if I'm right, if I'm pronouncing it correctly, thanks Glenn for the comment that everything is making sense so far. So good to know that. Okay. Okay.
I think you're good.
All right. All right. Yeah, because anyway, the objective is to give a window so that you can build on this thing. It's not like covering too many things without understanding. Even if we cover small things, but we should cover it in a way so that you can build up on top of it. And I'm sure the lab assignments, etc., in the beginning it will look little tedious, but by end of 2-3 days you will figure out that okay, this is how it is relatable. And Gem 5 has a learning curve, so don't get overwhelmed if things look at the beginning a little difficult, but it's worth that effort. Yeah, Arjun.
So ALU is also a hardwired controller. Oh.
So see, ALU will require some control signals.
Okay.
So here we are saying that so again, the control signal generation can be done in different ways. So one easy to understand way is hardwired control. So basically you build a hardware which will depending on the opcode will generate all the required control signals. So for example, the ALU, inside the ALU, if you look, you will see that it has a multiplier, it has a shift, basically shifter, it has a comparator, it has a different modules. Now, in this particular instruction, which module to be used? That has to be told to the ALU, and that will be told through some control signals that, okay, the opcode says that, okay, add. So you tell the ALU that you enable your adder unit inside the ALU, and accordingly it will generate the result.
Oh, okay, sir.
Yeah. All right then. Thanks everyone for your time, and I hope more and more students join, because it doesn't feel good to have less number of students, because with more students I think better interaction or more interaction will be possible. So do let your friends, if you know some of them, to attend, because this looking at the videos, I don't think is the best way to get things. Yeah.
Thank you, sir.
Thanks everyone.
Thank you, sir.
Thank you.
Thank you, sir.
Thanks. Bye bye.